Okay, now we will continue the second method. This method is not very practical. I mean, you cannot always pull a wire inside a magnetic field back and forth. Instead of using this, a more practical method is used. That practical method, second method, is inducing an electromotive force E in a loop or loops by changing magnetic flux. So the keyword in this title is changing magnetic flux. How can we change magnetic flux? We will check the equation. Equation of magnetic flux is A times B times cosine theta. If we want to make a change in magnetic flux, we can make a change in magnetic field intensity. We can make a change in area of the loop, or we can make a change in angle. What is angle? Orientation, change in orientation of the loop with respect to magnetic field. By these three methods, three ways, we can make a change in magnetic flux. As a result, we are going to observe and induce EMF in this loop. So now first I will talk about the change in magnetic field strength through the loop. The first one. By changing magnetic field strength through the loop, how can we induce an EMF? So to do that, to induce an EMF in a loop or loops of wire, move a bar magnet towards or away from a coil. So, in fact, I did this experiment with you before. So I am going to now move a bar magnet through or away from the coil. Now observe this, the galvanometer if there's a change. Now I'm going to make it closer. Yeah, I will make this bar magnet closer to the coil. Observe what will happen. When it make it closer or farther or closer or farther, as you see, there is a current. So the key idea is this. We are making a change in magnetic flux through this solenoid. We are making a change in magnetic flux through the solenoid. How? Okay, when bar magnet is away from the coil, just like this case. So number of lines crossing the area is less. How many lines are crossing the area now? Loop, area of the loop. Yeah, 1, 2, 3, 4, 5. 5. This case. But when I make it closer like this, second case. Now more lines are crossing the area. Count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 lines cross the area of the loop. So magnetic flux increased. So from this position to that position, which position? This position to that position, magnetic flux increased. I made a change in magnetic flux through the loop. While magnetic flux is changing through the loop, I observed that there is an induced current, there is an induced EMF in the loop. Or move it away. Move bar magnet away. So again, you are going to observe. This time, I did opposite. Now magnetic flux is maximum because it's closest. Then I pull it away, it decreases. When I pull it away, it decreases. So then we make a change in the magnetic flux through the solenoid. This change in magnetic flux induces a current in the solenoid. But when I keep closer, okay, at rest, maximum magnetic flux, do you see something? Nothing. Because I didn't make a change. Keyword, change. Change in magnetic flux, not magnetic flux. Change in magnetic flux. You can make a greatest magnetic flux. Right now, magnetic flux is greatest. Because I hold the magnet closest. But do you observe a current? No. Like we should make a change. Without making a change, you cannot induce an EMF. You cannot induce a magnetic. You can induce an induced current. So maximum magnetic flux, but there is nothing. But now what am I doing? Changing the magnetic flux. When I was changing the magnetic flux, you see that there is a current in the loop. So keyword in this section is change in magnetic flux through the loop. If you make a change in magnetic flux through a loop, If you make a change in magnetic flux to a coil, you are going to induce a current. By the time, sometimes I will say induce current, sometimes I will say induce EMF. They are related, according to Ohm's law. EMF means potential difference. If there is no potential difference, no current. Yes, potential difference, yes, current. For that, when I say induce EMF, don't think that I am saying two things. I am talking about both of them, because one of them exists, the other one also exists. Induce EMF exists, induce current exists. Okay, but be careful, caution. Plane of the loop must not be parallel to magnetic field lines when you are moving the loop. Right now, loop is out. This is the magnetic field lines from the top of the board to the bottom. And I hold the loop parallel to magnetic field lines, parallel to the board. Magnetic flux right now is 0, because there is no line crosses the loop. Right now, how much? Again 0. So if I hold the loop parallel to magnetic field lines so that I push it into, I make it closer or away from the coil. In this case, because you don't make a change in magnetic flux, there will be no induced EMF. So, I didn't rotate it. Did I rotate it? I'm saying that caution, the plane of the loop mustn't be parallel. If you move a loop parallel to the magnetic field lines, because magnetic flux is always 0, so there is no change in magnetic flux, there will be no induced current, there will be no induced EMF. But right now, I am holding perpendicular, right? What is magnetic flux right now?
Maximum.
No, 0, I am out. There is no lines crossing the magnetic field. There is no line crossing the loop. 0 magnetic flux. Now when I take it into what's happening, magnetic flux increases, huh? So from 0 to a maximum value. Is there a change in magnetic flux? Yes. In this case there will be an induced EMF. Which means if you hold loop parallel to the magnetic field lines, now magnetic flux is 0. Now 0 again. 0, 0, 0, 0, 0, 0, 0, 0. No change. No change in magnetic flux. No induced EMF. But if I hold it perpendicular, 0, maximum, 0, maximum, 0, maximum. I'm making a change in magnetic flux. So there will be an induced EMF. Now when you hold the loop perpendicular to magnetic field lines, so that you pull it in and out of the magnetic field region, so you are going to induce maximum EMF. If it is inclined, like this, okay, 0, still exists, but not maximum, of course. Yeah, induced EMF will be a little smaller than the maximum. And maximum, smaller, 0. No, maximum, smaller than maximum, 0. Suppose a woman wearing a bracelet that is unbroken ring of copper. Bracelet, similar to this loop, huh? It's a copper again. Unbroken ring means electric current can circulate in the bracelet, just like circulating in the stone. If she walks briskly, directly, quickly, into a strong magnetic field, while wearing the bracelet, how should the direction of the bracelet be with respect to the magnetic field in order to avoid induced current in the bracelet? How should we hold the bracelet with respect to magnetic field? Avoid means not to induce. So we have talked about this. If you hold loop parallel to the magnetic field lines, and then if you quickly enter inside this magnetic field, there will be no induced EMF because there is no change in magnetic flux. That's why you should hold bracelet parallel to magnetic field lines. It doesn't matter how quickly you enter or how slowly you enter the magnetic field, because there is no change in magnetic flux. Outside is 0, inside is 0, so no change in magnetic flux, no induced current in the bracelet, no induced current EMF in the bracelet. Again, this is a good question. Orientation of the bracelet with respect to magnetic field must be parallel in order to avoid induced current in the bracelet. Okay, so now look at the board. Second method is, in fact we talked about this one, but it's not second method, but this is going to be a little detailed study. Move a loop perpendicular to magnetic field in a uniform magnetic field. What does non-uniform magnetic field? What does non-uniform magnetic field mean? Intensity of the magnetic field is not constant, everybody. Different intensity. How can I understand this? Look at the separation between dots. In here, dots are closer, huh? But right there, dots are farther. And lines are farther, lines are closer. If the magnetic field lines are closer, it represents a stronger magnetic field. In here, magnetic field is stronger in this region. Then, from left to right, magnetic field intensity is decreasing. And you are pulling a conductor inside this magnetic field perpendicularly from left to right. While you are pulling this conductor, this loop from left to right, how does the magnetic flux? Is there a change? Yes. In here, because B is maximum, magnetic flux is maximum. Count 1, 2, 3, 4, 1, 2, 3, 4, 5. 5 times 4, 20. 20 dots crossing the area. In here, 3 times 5, 15 dots crossing the area. In here, 2 times 5, 10 dots are crossing the area. In here, 5 is crossing the area. So magnetic flux is decreasing while this loop is moving from left to right. So if there's a change in magnetic flux, should we observe there's an induced current? Yes. Keyword is what? Change in magnetic flux. If you are making a change in magnetic flux, there will be an induced current, there will be an induced EMF. Yes, in here magnetic flux is 20, in here 15, in here 10, in here 5. While this loop is moving from left to right, because magnetic field intensity is decreasing, magnetic flux also decreasing. And decreasing magnetic flux results in induced current in this loop. Now, next one is I am going to change the area. Remember, according to my magnetic flux equation, magnetic flux depends on magnetic field intensity B and also depends on area of the loop A. Now we will change the area. Changing the area A of the loop through which magnetic field lines passes. Now, but this magnetic field is uniform. It's a uniform magnetic field. How do I get it? Look at the separation between the dots. Separation between the dots are same everywhere. So this indicates that magnetic field is uniform in this region. Uniform in this region and constant in magnitude. Okay, now I'm going to hold the loop first outside the magnetic field region. So is there any magnetic field lines crossing the area? No. So no magnetic field lines crossing the area. Magnetic flux while is 0 now, is it? It is 0. Okay, now I will take this loop into the magnetic field. 0, area inside the magnetic field is 0. Now, area inside the magnetic field is a quarter. Is it increasing? Yes. Area inside the magnetic field is half. Area inside the magnetic field is 2/3. Area inside the magnetic field is completely new. So that while this loop is entering inside a magnetic field region, area of the loop, which is inside the magnetic field, is increasing. If area of the loop which is inside the magnetic field increases, magnetic flux also increases, correct? Now count how many lines are crossing the area. 3, huh? 3. Now 6. Now 9. So as I was pulling this loop into the magnetic field, magnetic flux is increasing. While in the outside, 0. 0, 3, 6, 9. So that's why as loop enters into the uniform magnetic field, magnetic flux increases. Is there a change? Yes. If there's a change, we are going to observe an induced current in the loop. A current will start circulating in this loop, and we are going to measure the induced EMF in this loop. Okay, now let's continue moving inside the magnetic field. This loop, what is the magnetic flux now? 3 times 5, 15, huh? 15. Okay, while I was moving this loop inside the magnetic field, what is the magnetic flux? 3 times 5, again 15. 3 times 5, again 15. 3 times 5, again 15. So number of lines crossing the area now, same. It's not changing. So, if no change in magnetic flux, no induced current, no induced EMF. And while you are pulling a loop perpendicular to a uniform magnetic field, inside a uniform magnetic field, because there is no change in magnetic flux, there will be no induced current in the loop, there will be no induced EMF. But magnetic flux is maximum. Remember the key word? We need change, not magnetic flux. Change in magnetic flux. So maximum, 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 maximum. All are maximum. All are maximum. No change. No change in magnetic flux. No induced current in the loop. No induced EMF. It can be measured across the room. So, as loop is moving inside a uniform magnetic field perpendicularly, no change in the magnetic flux, no current is induced in the loop, no EMF is measured. Okay, what about this? Let's take this loop out. Now magnetic flux is 9, huh? 9 lines are crossing. Now?
6.
Now?
3.
Now 0. So while I was taking this loop out, when I was taking it out, number of lines crossing the area decreases?
Yes.
Now 9 lines crossing this loop in my hand. Now 6. Now 3. Now 0. There's a change, decreasing magnetic flux, isn't it? So if there's a decreasing magnetic flux, it's a change, huh? Decrease a change. There will be, again, an induced current. You can measure an induced EMF. So then, summarize it. While magnetic loop is entering or leaving, while loop is entering and leaving to the magnetic field, entering to magnetic field region, or leaving out the magnetic field, we can observe an EMF because there is a change in magnetic flux. But as the loop is moving inside uniform magnetic field, because there is no change in magnetic flux, we cannot observe an EMF. We cannot measure a current. Okay, one thing be sure. In fact, we are not changing the area of the loop. We are making the change in area of the loop, which is inside the magnetic field in here. Yani, now complete out. Now a part of is in. Now a half of is in. Now completely. Yani, we are changing area of the loop, which is inside the magnetic field. But now, in second case, we will make a change in area. Decrease or change the area of the loop by grasping at opposite ends and stretch it. Right now area is at this guy. Now I stretch it. What happened to area? Area decreased, huh? Yani, while we are holding the loop inside a magnetic field, grasp it and then stretch it and make it decreasing area. This is a chapter 2 question about this. I'm going to now explain on this question. A flexible loop of conducting wire. Flexible means you can make a change in shape, as I did here. So you can stretch it, you can make it circle, it's up to you, so you can make a change in shape. A flexible loop of conducting wire has a radius of 0.12 meters. This is the case. A loop is inside a magnetic field, as you see. And the radius of this loop is given as how much? 0.12 meters. So this is R. Radius of the loop, 0.12 meter. And this loop is perpendicular to a uniform magnetic field. Perpendicular. So if loop is perpendicular to a magnetic field, magnetic flux is maximum, huh? We learned this section 1, chapter 5. Like as soon as you read this, you are going to say that yes, magnetic flux is maximum. maximum magnetic flux is measured. And we calculate it by area times magnetic field. No need to use cosine theta. Cosine theta is 1. Perpendicular to uniform magnetic field with a strength of 0.15 Tesla. So magnetic field intensity is 0.15. Let's record in here. B is 0.15 Tesla. As in figure, this is the figure. This figure is given in the book, in the question. You see the magnetic field lines cross into the boat. Loop is in the plane of the boat, so loop is perpendicular to magnetic field lines. The loop is grasped at opposite ends and stretched, as I did. The loop is grasped at opposite ends and stretched until it's closest to an area of 3 times 10 to the power negative 3 meters squared. And the final area, this area is how much? 3 times 10 to the power of, this is final area. Let me record in here. Final area equals to 3 times 10 to the power of negative 3 meters squared. But initial area is not given, I will calculate it. So initial area must be calculated. As in the figure B, as in here, it is closed. Calculate the change in magnetic flux. The change in magnetic flux, delta phi is the question in here. Delta phi, I will calculate it. Alright, what does delta phi mean? Any quantity delta means final value minus initial value. So delta phi means final magnetic flux minus initial magnetic flux. I know magnetic flux equation, A times B. So instead of final magnetic flux, I will write final values. Final area, A times, B is not changing, so just B. There is no change in B. Magnetic field is same. Minus initial magnetic flux, area initial times magnetic field B. So for both terms, which quantity is constant? B is constant. Common parenthesis of B, B multiplied by area final minus area initial. Area final is given. Only I need to calculate area initial. How can I calculate this area? This area is the area of a disk, right? And area of a disk is pi r squared. So I can calculate initial area by pi r squared. Now let's calculate it. So magnetic flux, change in magnetic flux is equal to B is how much? How much is B? 0.15. Bracket. How much is final final area? 3 times 10 to the power of negative 3. It's given in the question. Minus initial area is pi r squared. Pi is 3.14. 3.14 reduces how much? It's given 0.12 multiplied by 0.12 squared and close the bracket. The rest is your calculator. You are going to apply the calculator and you will find the answer. I think it is negative 6.33 times 10 to the power of negative 3 Weber. Okay, what does this negative sign indicate? Decrease. There is a decrease in magnetic flux. Magnetic flux is decreasing. Negative sign indicates that phi, yani magnetic flux, decreases. If it is positive, magnetic flux increases. If it is negative, magnetic flux decreases. Now third one, how can we change magnetic flux? Area, magnetic field, and angle. Orientation, changing orientation of loop, yani angle theta, with respect to magnetic field. Yani rotate the loop inside the magnetic field. While you are rotating the loop inside the magnetic field, you are changing the angle. You are changing the orientation of the loop with respect to magnetic field. Now, tell me, loop is parallel to magnetic field lines, huh?
Yes.
So magnetic flux is? Zero. Now magnetic flux is increasing. Now increasing. And now maximum. Now decreasing. Now zero. So while you are rotating a loop inside a magnetic field, you are continuously changing angle. you are continuously changing angle, you are continuously changing magnetic flux. So if magnetic flux continuously changes, what does it mean? You are going to induce EMF continuously. Yani push it forward, take it back, push it forward, take it back. It's not practical, huh? Hold the loop inside a magnetic field and rotate it. It is the best method. It is the method of generators. So all generators, loops are rotating inside a magnetic field and will induce an EMF. So third method is the most practical method. Rotating a loop inside a magnetic field so that you are changing magnetic flux continuously. You are getting the induced EMF in this continuously. Okay? About this, we have a chapter 2 questions. Okay, let's solve this. Chapter 2 question number 24. A bar magnet is attached perpendicular to rotating shaft. Okay, this is the picture. Rotating shaft is this. Those rod is rotating shaft. And the magnet is then placed in the center of the coil of wire. Yes, you see that? It is at the center in here, again at the center in here, again at the center in here. There's a bar magnet with N pole and S pole. In which of the arrangement could this device be used as an electric generator? Electric generator will study section 2, but the question is in fact asking you, in which case you can induce an EMF? Induce an EMF. Yeah, let's make a small change. In which of the arrangement could this device induce an EMF? In section 2, we'll talk about them. In section 2, of course, devices which produce induced EMF is called generators. So explain your choices. What we need to induce an EMF in a current loop? Change in magnetic flux. So we are going to now try to investigate in which case you are making a change in magnetic flux. You are going to study one by one. Okay, the first case is this. Loop is like this. Loop is like this. And according to the first case, N pole of the magnet is above, like this. S pole is below. You are keeping it like this. But you should rotate it in that direction. So, yeah, you are going to rotate this magnet like this. So now, magnet is parallel to the loop. Magnetic flux is 0. As I rotate this magnet like that, so what's happening? Magnetic field becomes perpendicular now. If the magnetic field is perpendicular, magnetic flux becomes maximum. So 0 magnetic flux, maximum magnetic flux, continue rotating, 0 maximum, 0 maximum, 0 maximum. So continuously you are changing magnetic flux. So if magnetic flux changes continuously, what happens? So there's an induced EMF. And this can be used as a generator. This can induce an EMF. Let's study this one, second one. In the second one, it is like this. N pole, S pole. Initially parallel to the loop. 0 magnetic flux. But if I rotate it like this, because this tells you, rotate it in a horizontal. Yeah, I have to rotate this bar magnet in horizontal plane. So 0 magnetic flux, because magnetic field is parallel to loop. But now, perpendicular. Maximum. Then, parallel, 0. Perpendicular, maximum. So, in this rotation also, magnetic flux is changing. So, if there's a change of magnetic flux in this rotation, of course, there will be an induced EMF as well. This is also a method of inducing EMF, so this also can be used as a generator. Third one. The third one, you are going to hold the magnet like this, but you are going to rotate it like that. Now, this is telling you that rotate it in a vertical plane like this. Now, you are going to rotate the bar magnet like this. Now, what is magnetic flux?
0.
Now, what is magnetic flux?
0.
0, 0. Yeah, rotating like this does not make a change in magnetic flux.
It remains
Yes.
parallel.
Yeah, always parallel. Yeah, magnetic field, the plane of the magnet and plane of the loop always parallel to each other. So because of that, there will be no change in magnetic flux. If no change in magnetic flux, No induced EMF. So in this one, we cannot induce an EMF. Okay, maybe you can use your page as a, you can use a potato loop, okay, your pen. Okay, first case is this one. Okay, let's do the first case. You are going to rotate your pen like this. Yani magnetic like this. Now initially pen is parallel to loop. But now perpendicular. Now parallel. Now perpendicular. This is the case, first case. Second one, you are going to, again, you have also magnet pen, your magnet, and S pole, N pole, and S pole. But this time you are going to rotate it like this, in horizontal plane. But still parallel, zero magnet. But now maximum. Now zero. Now maximum. Third one, you are going to rotate your pen, which is the magnet, like this. When I was rotating like this, I don't make a change in magnetic flux. Yani magnet is always parallel to the loop. Parallel. So when the magnet is parallel to the loop, magnetic flux is always zero. Is there a change in magnetic flux? No. No change in magnetic flux. No induced EMF.